In section 3.3, we're going to discuss the concept of orthogonality. If you think back to your earliest discussions of geometry back in elementary school, you'll likely remember that two lines are defined to be perpendicular if they intersect at a right angle. Now for vectors, this definition doesn't translate over perfectly. We can't quite use it as is, because remember that if I take two geometric vectors and I draw them, I can draw them far enough apart so that they don't intersect at all, no matter how long the vectors are, right? I can just draw them sufficiently far apart so that they don't intersect at all. So we can't refer to their intersection point in their definition because there might not necessarily be one depending on how they're expressed. But what we can do is refer to the angle that the two vectors form if they are specifically drawn so that they have coinciding initial points. At least we can do that for geometric vectors. So that's what we're going to start with. Let's start with two vectors, x and y, and we'll assume that they're both non-zero vectors in R2 or R3. That's really what it means to be geometric vectors. So whenever you have such vectors, you can always draw the following. I can always draw them so that they both start at the origin. They both have initial point at the origin. So let's start with that picture. We've drawn this picture a few times before, but this is the same one we want to have in mind for the definition that comes after. Okay, so I'll draw the terminal point of one of the vectors, and then I'll draw the terminal point of the other vector. So let's call this the vector x, and we'll call this the vector y, right? And I can always draw an angle between those vectors. As long as I draw them so that they both start at the origin, then they're going to form an angle when I draw them, and I can call that angle theta. And if you remember, why do we care about that angle? What was the first motivation for even considering it? Well, remember that the dot product of two vectors that are in R2 or R3 was originally defined by this rule. The dot product of geometric vectors x and y is defined to be the product of the norm of x with the norm of y, and then multiplied by the cosine of the angle between them. Right, where the theta in this calculation is this angle down here. So that's why we originally cared about this angle. But now I want to remind you that this is one of the things I said towards the end of the last section, that we always take the angle theta to be between 0 and pi. Right, so it's in this closed interval. It could be 0 and it could be pi, or it could be something in between, but it cannot be less than 0 and it cannot be greater than pi. So let's draw the graph of cosine over this interval right here. So what does cosine look like on that interval? Well, I'm just going to draw it over here. So it's going to look something like this. We've got the x-axis, or actually, how about I call it the theta axis? Okay, and then we call this the y-axis, because really we're drawing the graph of cosine of theta over the interval 0 to pi. So it makes sense to call it the theta axis, not the x-axis. So let's say from 0 to pi is that interval there. So I'll call this pi, and then the midpoint, right in halfway in between, would be pi over 2. Okay, so that's my labeling. Now if I draw, and I need a point 1 and negative 1 on the y-axis, because cosine is trapped between positive 1 and negative 1. So it looks like this. Really what we're drawing is the first half of the cosine wave. So it starts at positive 1, it goes down, it hits the theta axis right at theta equals pi over 2, and then for this other segment it's going to now go all the way down to a minimum of negative 1, right at pi. If you go cosine of pi, you're going to get negative 1. So that's the graph of cosine of theta, or y equals cosine of theta, over the interval 0 to pi. So we're going to come back to this picture in a moment, but now let's actually talk about how we can actually define what it means for these two vectors x and y to be orthogonal. Well, if you have this picture, it's easy to do. You just define those two vectors to be orthogonal if this angle theta happens to be a right angle. So if you're measuring angles in radians, which we are, then that just means the angle is equal to pi, theta is equal to pi over 2. So that's our definition for geometric vectors. Two non-zero vectors, x and y, in R2 or R3, so in other words, they're geometric vectors, are called orthogonal. Or you can use the word perpendicular if you like. So left room for that word as well, so we can say perpendicular. If the angle theta between them is equal to pi over 2. So that's the definition for two geometric vectors to be orthogonal. And I've required here in this definition that they be non-zero. The reason for that is because if one of them was 0, let's say y was equal to the 0 vector. Remember what that means geometrically. That means the terminal point of y and the initial point of y would be the same point. That would mean y has no length. So if you take this point and shrink it all the way over to the origin, well, then the only vector you're going to be able to see is the vector x. And this angle theta won't really be formed, and it won't make sense to even refer to it. So that's why we have to restrict ourselves to the case where both of the vectors are non-zero, at least for now, for this definition. But just like with the definition of dot product, we're going to seek to improve it so that we don't have to rely on that restriction. And that's what we're going to do by the end of this page, actually. So if you go back up and look at the original dot product formula, if I were to isolate cosine of theta, so if I just solve this for cosine of theta, I would get this. I'd get cosine of theta is equal to the dot product of x and y divided by the length of x times the length of y. Right, that's what I would get if I solve, that's what I would get if I solved this equation for cosine of theta. I would get this right here, right? Just take the length of x and the length of y, just divide them over to the other side, and this is what you would get. Now, the next remark says that it follows that the dot product of x and y is equal to 0 if and only if cosine of theta is equal to 0. Well, why is that true? Well, if cosine of theta is equal to 0, then you really have a 0 on the left-hand side of this equation. You could just multiply the lengths up to the other side, and it would still be 0 on the left-hand side. So then you'd get the dot product of x and y is equal to 0. So that's why if you assume this equation is true, then you're going to conclude that this equation is true. But on the other hand, if you assume that this equation is true, if you assume that the dot product of x and y is equal to 0, well, that means the right-hand side of this equation has a 0 for the numerator, which means you have cosine of theta is equal to 0 divided by some number. In other words, cosine of theta is equal to 0. So for that reason, if you assume that this equation is true, you can conclude that this equation is true. So really, they are true under the exact same circumstances, and that's why we can say that this equation is true if and only if this equation is true. So, but when is cosine of theta equal to 0? Cosine of theta, we have the graph up here, that's actually why we drew it. Cosine of theta is equal to 0 right when theta is equal to pi over 2. So really, and that's the only point in the interval 0 to pi where cos of theta is equal to 0. So the point here is that the dot product of x and y is equal to 0 exactly when theta is equal to pi over 2, or in other words, when the vectors x and y are orthogonal. And that's why we get the following conclusion that I haven't shown you yet, but I'm going to slide this up now so you can see. This is called the test for orthogonality. Two non-zero vectors, x and y, in R2 or R3, just summarizing what we already started with, right, are orthogonal if and only if, well, we could say that the angle between them is equal to pi, or we could just say if their dot product is equal to 0, because as we just observed, that's the same thing, or at least that's logically equivalent. So that's how we can finish this off. That's how you can finish off this test. They're orthogonal if and only if their dot product is equal to 0. Now, that test only works when x and y are both non-zero vectors in R2 or R3. But really, it really isn't fair to expect any more than that, because the definition for orthogonality so far also requires that you're referring to two non-zero vectors in R2 or R3. So based on this test, we can generalize the definition of orthogonality very nicely. Why don't we just make this the definition of orthogonality? And since this dot product relationship, this makes sense for any vectors in any dimension. You can talk about vectors in R4, R5, R6. You could still talk about what it means for the dot product to be 0. So we could just use this as the definition of orthogonality, and that will allow us to improve this definition, which is actually quite restrictive, right? This definition currently only applies to geometric vectors in R2 or R3 that are both assumed to be non-zero. But we can drop both of those restrictions just by changing the definition. We're not really changing the definition, we're just expressing it differently in a way that generalizes to higher dimensions. So we'll take this to be our new definition for being orthogonal. So what it says here, this allows the definition of orthogonality to be extended to higher dimensions, and that's what we're going to do down here very concisely. So two vectors, x and y, in Rn, where for any dimensional space, so they could be higher dimensions than 3 dimensions or 5, or they could be 10 dimensions or 12 dimensions, whatever. They just have to have the same number of coordinates. They both need to be in the same dimensional space. So two vectors x and y in Rn are orthogonal if their dot product is equal to 0. Okay, and this is the definition that really matters. So I'm going to put a box around it, even though I don't usually put boxes around definitions. I know it can sometimes get confusing because we've defined orthogonal twice on this page, and that can be confusing. But the important part to know is that this definition applies to any higher dimensions, but the original definition only works for geometric vectors in R2 or R3. But as we've seen, if you happen to have geometric vectors in R2 or R3, you can use this definition, or you can use this definition down here, and they'll be equivalent. So we're not changing anything that was already set up by introducing this definition. We're just making it easier to check and easier to talk about.